All right, welcome to the Explainer. We interact with our digital devices literally all day, right? And it's so easy to just marvel at the seeming intelligence of AI. But today, we're pulling the curtain all the way back. We are taking a journey straight down to the bare metal of our machines. We're moving way past those friendly chat interfaces and diving right into the cold, rigid physical reality of silicon. So get ready because we're going to challenge some of your most basic assumptions about how computation actually works.
Okay, let's dive into this. I want to kick things off with a perspective-shattering question. Do computers actually process meaning? Just think about that for a second. When you type up a prompt or ask an AI some complex question, it intuitively feels like the machine grasps the intent behind the words you're feeding it. I mean, the output makes sense to us, right? But the wild reality is that intuition is entirely backward. Down at the meta level, the machine is completely blind to human meaning. It literally only understands the pure physics of electrical resistance and discrete voltages.
And it gets even crazier. Consider this staggering statistic. 80 to 90% of modern AI compute cycles are actually just hardware-level approximations. Really wrap your head around that for a minute. When these massive language models are doing their heavy lifting, they aren't actually delivering exact mathematical truth. They are fundamentally just guessing the nearest answer, so they can process oceans of continuous data at breakneck speeds. That flawless mathematical certainty we all think powers our digital world, it's largely an illusion. To understand why this massive guessing game is happening, we really have to look at the severe physical divide between us and the machine. On one side, you have human cognition, what researchers playfully refer to as OS alpha. It's warm, it's highly associative, and beautifully messy. It's kind of like a rambling Monday morning coffee thought, right? It's a continuous flow. But on the exact opposite side, we have the computer's physical hardware. This is dry code, it is freezing cold, strictly deterministic, and demands absolute exactness. The microchip doesn't care about nuance or feeling. It operates on a relentless, unyielding metronome of clocked voltages. Because of this massive divide, generative AI isn't some independent, conscious thinker. Honestly, it operates a lot like the babblefish from sci-fi. It's just a mechanical translator. Deep inside an AI, concepts float around in continuous vector spaces, sort of like a fuzzy multidimensional map of meaning. But the AI is just blindly orchestrating discrete tokens across those spaces without actual comprehension. It translates your English prompt into Python code or maybe some pixel data without understanding a single word of it. It is purely mapping input to output. So how exactly do we force our beautifully messy, flowing thoughts into that rigid binary grid? Well, we have to squeeze them through a hidden translation layer known as the tokenization bottleneck. Before a neural network even begins to look at human language, it uses a compression algorithm called byte-pair encoding to violently crush our flowing thoughts. It basically scans text and merges frequent adjacent characters into discrete numerical IDs. The machine simply can't read our language. It can only process these violently compressed, rigid little chunks. And this arbitrary chopping creates devastating logical vulnerabilities. Take the continuous, holistic concept of pi. To an AI forced through this tokenization bottleneck, that mathematical concept is completely shattered into arbitrary, meaningless subwords, a 3, a decimal point of 14, and a 159. Because those arbitrary boundaries don't align with systematic decimal logic whatsoever, the machine's ability to learn real arithmetic is basically destroyed right out of the gate. It's not doing math, it's just memorizing arbitrary strings of text. This arbitrary chopping creates what researchers call a severe modality gap. And we see the symptoms of this logical collapse everywhere. For one, it's why these multi-billion-dollar models completely lack basic spelling abilities. They never actually see letters, they only see compressed token IDs. Even worse, we see massive multilingual fragmentation. Because this tokenization was historically optimized for English, languages like Arabic or Hindi suffer terrible token inflation. If you're operating in a non-Latin language, you literally pay higher compute penalties and get slower speeds. All because of this arbitrary software fragmentation. So the software is violently chopping up our intent. But let's transition even deeper down the computational stack. We need to examine the microscopic hardware responsible for this grand computational illusion. Because underneath that whole tokenization bottleneck, the physical microchips themselves are making compromises that literally destroy digital truth. To really anchor this massive hardware flaw, we have to look at this quote from Kyle McLean-Smith. He puts it perfectly. It's fundamentally an approximation system, not real arithmetic. That perfectly sums up the reality we're dealing with here. The physical engine driving your incredibly advanced AI isn't calculating absolute ground truth reality. It relies entirely on highly educated guesses that are burned right into the silicon of the machines.
Meet the true antagonist of our hardware story, the floating point unit, or as we like to call it, the FPU Gambler. The FPU is specifically designed to approximate heavy, complex math incredibly fast. But here is the massive catch. To achieve that blistering speed, chip manufacturers literally burn their own proprietary, completely secret seed tables right into the silicon. It's fast, absolutely, but it's incredibly lossy and totally unauditable. It's basically like a gambler frantically throwing darts at a board to guess the nearest answer.
And relying on this FPU Gambler leads to something experts call the wood chipper effect. Here is exactly how that goes down. Step 1. The AI ingests exact source data, say a copyrighted book. Step 2. The FPU hardware approximates the math of that data using those secret silicon tables. And step 3. Because that math was just a guess and not a precise calculation, the original data provenance is lost forever. The FPU acts like a giant blender. You know exactly what fruit you tossed in, but there is absolutely no way to reverse engineer that smoothie back into the exact fruits it came from.
Now, this microscopic hardware glitch scales up into a massive, real-world nightmare, the liquidation of contributors. When the gambler approximates data, the exact mathematical path of that data is wiped out. You completely lose the copyright chain of title and the identity of original human creators. If you're a writer, an artist, a coder, your footprint is scrubbed clean. We are moving toward a future where AI handles high-liability tasks, and you simply cannot build verifiable digital trust on a legal foundation that is fundamentally just guessing and destroying its own footprints.
But hey, take a breath. It's not all doom and gloom. We absolutely do not have to accept this lossy, untraceable system as our permanent reality. Let's pivot this explainer to the optimistic side, the innovations that can actually repair these architectural constraints, bypass the gambler entirely, and restore undeniable truth to our machines.
Let's start with fixing that software tokenization issue. Enter the Byte Latent Transformer, or BLT. And this brilliantly illustrates the path forward. Instead of relying on those rigid, pre-calculated dictionaries that shatter our words, the BLT dynamically reads raw, uncompressed bytes. It matches the performance of standard models, uses up to 50% less computational power, gives us 0 out-of-vocabulary errors, and completely fixes that unfair multilingual fragmentation. It literally reads reality as it actually is.
Now, let's see how this fix builds all the way down into the hardware layer. We need to replace the chaotic FPU Gambler with our deterministic hero, the ALU surveyor. While the Gambler relies on probabilistic guessing in those secret C tables, the arithmetic logic unit, the surveyor, deals strictly in 100% exact deterministic hardware truths. 1 + 1 is exactly 2 every single time on every single machine on Earth. It delivers absolute, globally accountable mathematical receipts.
So, the crucial point is, how do we connect our messy, imaginative minds directly to this exact hardware surveyor? Well, we use what's called the semiotic bridge. This is the universal deterministic interface of structured text, stuff like C code or JSON. Text isn't just for reading, it's a script that safely compiles our fuzzy human intent into rigid hardware execution. By utilizing this semiotic bridge and intentionally shifting our math entirely away from the FPU over to the exact ALU, we can completely bypass those sloppy approximations and finally restore forensic accountability. We've seen today how forcing the infinite, flowing complexities of human language into rigid mathematical boxes just fractures an AI's ability to reason. But innovations like the Byte Latent Transformer and relying on the absolute truth of the ALU surveyor show us a much better traceable path forward. So I'm going to leave you to ponder this final provocative question today. Is the messiness and continuous nature of human data really a bug we need to compress away? Or is it actually the ultimate vital feature our AI needs to unlock true reasoning? Thank you so much for joining me for this explainer. Keep questioning the systems you rely on, and as always, keep learning.